Okay, so now we have seen some basic functions. We will look at more functions in future lectures. We will also program some of these in the demo session and see how it works. We introduced the value at position function earlier, and that is equivalent to the built-in operator bang bang, which I mentioned. So positions in a list are indices, if you will, positions slash indices are numbered from 0 till n minus 1, where n is the length of L. And L bang bang j is the value at position j of the list. So if I have the list 2, 4, 6, 8, L bang bang 0 is 2, L bang bang 1 is 4, and if I try something like L bang bang 6, I will get an error, runtime error. Or even L bang bang minus 2, that is also a runtime error. And accessing position j is not a constant time thing, unlike arrays. Because this bang bang is nothing but just the function value at position that we defined earlier, and as we saw there, value at position n of x colon x's is nothing but value at position n minus 1 of x's. So you are stripping away one element after the other from the beginning of the list until you have stripped away n minus 1 elements, and at that point whatever element you are left with, you will return that. Yeah, so you need to peel off the applications of the colon operator, whereas in arrays and other languages, and also in Haskell, there is an arrays in Haskell also, which we will look at much later, that those things allow constant time access to any position in the list, but not so with these lists. Okay, so now we get to one of the most important notations with lists, because for writing examples and so on, this is what you will mostly use. You cannot write lists like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all the way till 100 when you try to run a command in GHCA. Rather, you would want a shorthand to write all numbers from 1 to 100, and that you do by saying 1 dot dot 100 or 0 dot dot 99 or whatever, right? And this is very similar to what you write in high school and sets. You will write 1 comma dot 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 100, right? So instead of 3 dots, we use 2 dots and there is no comma in between. Okay, so that is the important thing. Just like high school notation, use square bracket instead of braces, 2 dots instead of 3, no commas. Okay, but that is just some syntactic thing. It's meant to very closely mimic the high school notation that you are used to. Within braces, 1 comma dot 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 comma 100. That's what you would write in a math class. Here you would just write within brackets, you would write 1 dot dot 100. Okay, and this stands for the list m plus 1, m plus 2, and it need not just be start with 1 or 0 or whatever, it could start with any number. So you could even start with a negative number. I could have minus 22 dot dot 3, and then that would just be the list consisting of minus 22, minus 21 dot dot all the way up to 3, 0, 1, 2, 3. Yeah, so what happens if m is greater than n? So if I write something like 10 dot dot 0, I will just get the empty list. Okay, because you are supposed to start from a smaller element and work your way to the higher element. That is the point of this notation. So 1 dot dot 7 will give you 1, 2, 3, 4, 5, 6, 7. 3 dot dot 3 will just give you the singleton list 3. 5 dot dot 4 will give you the empty list. You can also skip values, just like in school you write arithmetic progression, you would write 2, 4 dot 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 100 means 2, 4, 6, 8, 10, 12, etc., etc., all the way till 100. What you are doing is you are giving the first element, you are telling how many elements to skip to get to the second value, and then you are you have to skip so many values to get to the third element, etc., etc. Okay, so that is arithmetic progression. So if I say 1, 3 dot dot 8, I will do 1, 3, the next element is 5, the next element is 7. Then the element after 7 that I would want to include is 9, but 9 is greater than 8, so I will skip it. Okay, I keep on going till I cross the value 8 that has been specified here. Okay. Here is another example, 2, 5 dot dot 19. So here I am skipping 3 values at a time. So I will have 2, I will have 5, then 5 plus 3 8, 8 plus 3 11, 11 plus 3 14, 14 plus 3 17, 17 plus 3 is 20, but that is beyond 19. So I will stop at 17. And the nice thing is that you can also have different descending sequences. I can have 10, 9 dot dot 10, 9, 10, 9 dot dot 0. And that will give me 10, 9, 8. This is a very common mistake, very common, this is a very potential for a very common mistake. You should take care. Quite often, you would just write 10 dot dot 0, thinking that you will get all numbers from 10 to 0, but this will give you an empty list instead. Okay, so if you want a descending list, you should remember to put the second element. Okay, just putting 10 dot dot 0 will just give you the empty list. Here is another sequence, 8, 7 dot dot 5 will give you 8, 7, 6, 5. That is just a descending sequence, but I could also do something like 12, 8 dot dot minus 9. Here I am decreasing the number 4 each time. So I will get 12, 8, 4, 0, then decrease 4 from that, that is minus 4, minus 8. The next element would be minus 12, but that is on the other side of minus 9. So if I start from 12, I go to minus 9, and then I have the number line here, I have 0 here, I have minus 9 somewhere here, minus 12 is here, 12 is there. So I start from 12, I cross 0, I go all the way to minus 9, and I have to go beyond to get to minus 12. So at this point I will stop. Okay, so I will stop at minus 8. This is the point at which I will stop. Okay, I will stop at minus 8. So in general, you can have the general pattern is a plus d dot dot b. Okay, and the d can be negative also, right? And then what will happen is that you will add d to each value in turn till you go past b. Okay, going past b means going below b if a is greater than b, or going above b if a is less than b. Okay, here is another perhaps even more useful notation, which is called list comprehension. And this is also something very familiar from high school mathematics. You would say something like x squared such that x belongs to the set 0 dot dot 4, and maybe I don't know, you want to say x is less than or equal to 10. Okay, these are the kinds of things that you would write, right? X is 0 to 4 means 0, 1, 2, 3, 4, and x squared means 0, 1, 4, 9, 16, yeah, right? And if I only want to list out those things that are less than or equal to 10, I will actually get the set 0, 1, 4, 9. That's it. Okay. So this is the kind of thing that you can do in Haskell also, except that instead of using braces, you will use square brackets, and instead of using the belongs to symbol, you will use using your keyboard whatever symbol will closely approximate it, and that is the left arrow, not the left arrow. You would actually press the left less than symbol and then the hyphen. Okay. And that will give you this. Yeah, so in mathematics you would write things like m, the set m equals all x squared such that x comes from L and x is even. Whereas in Haskell you would write the same, this generates a new set m from a given set L. In Haskell you would write almost verbatim except for a change of syntax, some superficial changes in the syntax. Instead of braces you use square brackets, and instead of belongs to, this is actually less than followed by hyphen, but I am using some special font for these slides which will fuse them together and put it like the left arrow symbol. So this is not left arrow, that you should need to remember, because left arrow is not a typable symbol on the keyboard. If I just do left arrow, it will go left. Okay, fine. So, but this is the point. So, you use m equals x raised to the 2 within square brackets, and then you use the same thing. Here you will use this vertical line, you use the same vertical line here, and then x belongs to L such that even of x holds. So, you can have, for instance, you can compute the divisors of all the divisors of x in a simple manner like this. Divisors of x is nothing but y, such that y comes from 1 to x. Let us say you want to only consider the positive divisors of x, y comes from 1 to x, such that x mod y equals 0. Once again, this is my, for the slides I am using a special font, but this long equal to here is actually equal to. If you were to type it on your keyboard with whatever system you are using, it will just be equal to, but I am using some special fonts that is making it a long equal to. Okay. Okay, so divisors should be simple. All numbers from 1 to x such that x mod y is equal to 0. Those are all the divisors of x. Let us look at all primes below x. Okay, so you want to look at all y such that y comes from 1 to x, such that divisors of y equals 1 comma y. That's it. So when is x is a prime or y or whatever, any number right. This is a very simple way of specifying what primes are, but this is also a program. It looks almost like you have written the mathematical definition of what a divisor is, what a prime is, etc. But these are also executable programs. We will see actually in the demo session that you can just write this, and that's a program that will run, and it will actually compute all primes below 100 or below 1000 or whatever you want. Okay, so list comprehension is very interesting and very powerful. You can, in mathematics, you can again write, for instance, you can write x squared plus y squared such that x comes from the, so some m is the set of all x squared y plus y squared values such that x comes from k and y comes from L, and maybe some other condition holds, and GCD of xy is 1, let us say. You could do this, right? Something similar can be done in Haskell also, right? And the point is that there are multiple generators, meaning that you build the set M not from just from one base set K, but from K and L. Similarly here, you build, here for instance, you can build the set of all pairs of integers below 10. X comes from 1 dot dot 10, y also comes from 1 dot dot 10, but you have to specify them separately. Pick each x from 1 dot dot 10. For each x, pick each y from 1 dot dot 10, and then you print all the xy pair values. So you should remember that the order of the generators matters. This is called a generator. This whole expression, x belongs to 1 dot dot 10, y belongs to 1 dot dot 10, both are generators. Okay, and what it really means is, for, think of it as a nested loop like this, for x in 1 dot dot 10, for y in 1 dot dot 10, xy. This is the value that you know. For each x in 1 dot dot 10, fix an x and then run through all y in 1 dot dot 10 and you should return the pair x comma y. You could of course reverse the order also. You could very well also say for y in 1 dot dot 10, for x in 1 dot dot 10 return xy. That's a different list of pairs. Okay. So here for instance, this will give you, this is like nested loops as I told you. Later generators move faster, but you will have to do many iterations of the later generators, one for each value of the first generator. Okay, so this will first give you 1 1 1 2 1 3 dot 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 all the way till 110, then 2 1 2 2 2 3 dot 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 all the way till 210, and so on till it comes to 10 1 10 2 dot 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 all the way to 10 10 comma 10. Okay, so this is list comprehension using multiple generators. Here for example is all Pythagorean triples below 100. What's a Pythagorean triple? It's recall that Pythagoras theorem says that square of hypotenuse square of the two sides, side 1 plus side 2, or in other words, xyz is a Pythagorean triple if x squared plus y squared equals z squared, right. So that's what I want to check. So now you see that you have a generator and you also have a filter, if you will. There are 3 generators and also a condition or a filter. Okay. So I pick x from 1 to 100. For each fixed x, I will pick a y from 1 to 100. For each fixed x and y, I will pick a z from 1 to 100. I will check if x squared plus y squared equals z squared. If so, I will output the triple, otherwise I won't. But now there is a problem with this. The problem with this is that I will repeat many triples. They will in actuality be distinct triples, but the content is not different. For instance, I might repeat 3 4 5. I might have 3 4 5 in the list, but I will also have 4 3 5. Yeah, I don't want this. I might want some 3 4 5 and 4 3 5 are more or less the same Pythagorean triple. I only want to list one of them, let us say. Then I can do it. What I can do is I can say what I can say is that order my triples in the way, in order that x is less than y less than z, or x is less than or equal to y less than or equal to z, you can say, but it will never be, it will not be a Pythagorean triple if x is equal to y, but you don't need to worry about it. You can put this condition. So you can take the same definition and you can put this condition. Then you will avoid repeating 3 4 5 and 4 3 5. You will only add 3 4 5. You won't list. You won't add 4 3 5 as part of the list. But even then, it is wasteful work because you are actually going through 100,000 1000 into 100, 100,000 triples. Here you don't do so much, you don't save too much, but you save a little. So you fix a value of x and you know that I don't even need to look at values of y smaller than x. So you generate the second, y comes from the list x plus 1 to 100. This is the important point. This generator, the point is, and z comes from y plus, the values of z come from the list which is all elements from y plus 1 to 100. So, the point is later generators can mention earlier variables. This is important. So, I will consider the list, I will consider x from 1 to 100, I will consider y from x plus 1 to 100, I will consider z from y plus 1 to 100, and then I will just check if x squared plus y squared is equal to z squared. If so, I will output that triple. Okay. So, this is another way of generating this. Yeah, and now many more useful functions can be built using this, using list comprehension. There is a nice function called concat, that if you give it a list of lists like 1, 2, empty list, 4, 5, 7, 9, 16, 25, let's say. So, this is a list that consists of 4 lists. Each of those lists consists some different expressions, some different number of expressions. That does not matter. But the point is that it will put all the lists in one sequence and make one list. So, you will, this concat of this will actually return the list 1, 2, 4, 5, 7, 9, 6, 25. And you can actually express concat using list comprehension. You say list out all values of x such that L comes from else and x comes from L. Okay. Recall the Haskell convention that whenever you use a variable to denote some single element, and when you have to denote a related list, you will use that variable followed by an s. So, if you have a list with one element and many elements later, you will call it x colon xs. Okay. Xs is the plural of x. Similarly, here you have a list of lists, so you will call it else. Since you want to call each list as L, we will call this list of lists as else. So, I will fix each list from else, and once I have fixed a list, I will look at each element of L and I will output that element essentially. So, I will get this. Okay. I can also have more complex things. Given a list of lists, I can extract the head of all the even length non-empty lists. This is nice. So, I am saying head evens of else is a list of lists. I am extracting the head of L such that L comes from else, length of L is greater than 0 and length of L is even. But once again Haskell GHCI will issue a warning if you use head. So, what do? You can actually use even these list generators. It is not necessary, it is not mandatory that you only use a single variable, you can also use patterns, to the left of this left arrow. So, how would you do it? You will just say return all x such that x colon something belongs to else, and I do not need to check that length of L is greater than 0, because x colon something is a pattern that is the pattern for non-empty lists. So, since I am only extracting x colon empty, that is automatically non-empty. So, I do not need to check this length of L greater than check. Okay. So, I can skip that check, and then I will just say even of length of okay. So, that is the code that has been given next, right? X, print out all x, list out all x such that x colon xs belongs to else and length of x colon xs is even. Now, I will introduce a small trick here, which is something called @patterns. When you use patterns, it is very nice to be able to use @patterns. What these allow you to do is to refer to the same thing by multiple names. So, here for instance, I am using x colon xs here and I am also using x colon xs here. I could perhaps simplify it by saying print out x such that L belongs to XS, but L also has another name, an alias, which I will call it X colon underscore. In other words, I want to refer to the first element of L as X, okay, but I also want to be able to refer it as L. So, X such that L, in other words, X colon underscore belongs to XS, belongs to Ls, and even length of L. So, notice that I am referring to L directly here, but I am also referring to the parts of L when I say X here on the left hand side. Okay. So, yeah, so now we are heading deeper and deeper into Haskell, and in this lecture we have introduced quite a lot of functionality, especially lots of convenient built-in functions and very convenient list notations, both the dot dot notation and the list comprehension notation that Haskell provides for the users. I will stop this lecture now. We will look at more, we will look at other stuff, and we will look at more lists in the demo session. Thank you.